Hi guys, so I'm here to show you how to do the problems that I assigned from section 3, that tab 3 in the reading. So just kind of a little bit of a review. Number 9 and 10 kind of lead up to the problems that you were supposed to do. And so number 9 says write down the equation that relates to heat and define all of its letters. So the calorimetry equation, so that is the Q equals C times M times delta T, which is what we're going to be using today. And below it's heat energy is Q, C is specific heat, M is mass, and delta T is change in temperature. Notice down below I say when talking about thermal energy absorbed by the system, heat energy is called enthalpy. And a change in enthalpy is the opposite sign of Q, which is your heat energy. So delta H is what's going to be represented with your enthalpy. So I'm just going to add that in there so you guys know, and it's right there on the sheet that you can see. Then number 10 asks you, what are the Q values for endothermic and exothermic reactions? Are they positive or negative? So Q is positive and delta H is negative for exothermic reactions. So that's when heat is leaving a system. And Q is negative and delta H is positive for endothermic reactions. So just know that pretty much delta H is the opposite. It's the reversible reaction of whatever you're looking at with the transfer of heat. It's usually, so if you're, again, ice cube in water, a glass of water, the heat energy from the water is going into the ice cube. So one is going to be positive, one is going to be negative. And your Q for the water is going to be exothermic because heat is leaving. Your Q for the ice cube is going to be negative because it's an endothermic reaction. Okay. So it is absorbing heat. So on to the problems. Let's look at the right-hand side of my paper my screen as we look at number 11 on your paper. So number 11 stated a calorimeter holds 75 grams of water at 26 degrees Celsius. A sample of hot copper is added to the water. The final temperature of the water and copper is 39 degrees Celsius. What is the change in heat associated with the change in the water's temperature? The specific heat capacity of water is 4.19 joules per gram degree Celsius. All right, so for all these problems, we're going to need either the equation Q equals M times C times delta T, or delta H is equal to negative C, or I should start off with mass times C times delta T. Okay, so those are going to be your two equations that you use there. So notice that if Q is positive, our delta H is going to be the negative version of that same exact equation. So number 11, you have some givens in the problem that are provided to you. First of all, you're given that the mass is equal to 75 grams of water, right? You're also told that your delta T is going to be 39 degrees Celsius minus 26 degrees Celsius to equal 13 degrees Celsius overall. And you're also told in the very last sentence that your specific heat is equal to 4.19 joules per gram degree Celsius. So the question that we are trying to figure out here specifically is, what is the change in heat? Okay, so what is the change in heat? So That is delta H. Whenever you see the keyword change, you're going to use the delta H equation. So delta H is equal to negative mass times specific heat times delta T. So the next thing I want to show you is what kind of reaction is going on here. So just to kind of get you guys thinking, right? We have a beaker full of water, and that beaker full of water then has a hot piece of metal, copper, placed into it. So what's happening? Well, if the metal is hot and the water is colder than it, then the heat energy from the metal is going to be going out into the water, right? And so if we think about that in terms of endothermic and exothermic, water in this case is going to be endothermic, right? And metal is going to be exothermic, okay? So that's kind of just a visual of what is going on here. Next, let's plug in our values, right? So our values for this are 75 grams times our C value, which is 4.19 joules over grams degrees Celsius, times our our 13 degrees Celsius. Now, don't forget your negative out in front of this entire equation, okay? I like to extend out my fraction line so I know what cancels out, which is degrees Celsius and grams. We're left with joules. When I plug this into my calculator, I get negative 4,085.25 joules. Rounded, that's going to be 4,100 joules. Okay, so that's your final answer for number 11. Let's look at number 12 on your problems. Number 12 says a chemist heats a 215 gram sample of iron from 25 degrees Celsius to 90 degrees Celsius. How much heat did the iron absorb? So that's what we're trying to solve for. The specific heat capacity of iron is 0.45 joules per gram degree Celsius. So in this problem again, I like to write out what are my knowns, right? My knowns, I have mass is equal to 215 grams of iron. Iron symbol is Fe. My delta T is going to be equal to 90 minus 25, which is going to get me 65 degrees Celsius. And then the C value that they give me is 0.45 joules per gram degrees Celsius. Okay, so now what are we trying to figure out? It specifically asked in the problem, how much heat did the iron absorb? And if we go back and look at the equations, the two equations at the very top of the sheet, heat is going to be Q, not change in heat, just Q is heat, okay? So the equation I'm going to use for this problem is Q is equal to C times M times delta T, okay? So plug in my values. I have for C 0.45 joules per gram degrees Celsius times my mass, which is 215 grams, times my delta T, which is 65 degrees Celsius. Extend out my fraction line, and I can see that my grams are going to cancel, my degrees Celsius are going to cancel, and I'm left with joules. After I plug this into my calculator, I get 6,288.75 joules, which that's going to round to 6,300 joules. Okay. All right. The next problem that we have here is number 13. And number 13 says, a 7.20 gram of mysterious substance was heated from 22 degrees Celsius to 84 degrees Celsius using 123 joules of heat. To identify the substance, we need to know the specific heat capacity of it. What is the mysterious substance's specific heat capacity? All right, so I'm going to write down my knowns again. So the knowns that I have for this problem are a little bit different than the previous problems because we're not solving for delta H or Q. Okay, so in our mystery substance, we know that the mass is equal to 7.20 grams. We have a delta T equal to, we started off with 22 degrees and we ended up with 84. So 84 minus 22 gets me 62 degrees Celsius. My C value, I don't know what that is. That's what I'm trying to figure out. And we were told that the heat that was used in this problem was 123 joules, right? So now I'm going to go ahead and use my equation, the same one as the previous problem. Q is equal to mass times specific heat times delta T. I'm going to plug in my values that I have. I have 123 joules is equal for my Q value. My mass is 7.20 grams. I don't know what my C value is, and I have a change in temperature of 62 degrees Celsius. So I need to get C by itself. So in order to do that, I'm going to divide everything on the right side that is not C. So 7.20 grams times 62.0 degrees Celsius. Anything I do on the right side, I have to do on the left side. So 7.2 grams times 62 degrees Celsius, right? This is going to cancel out on the right-hand side. On the right-hand side, I'm left with C. C is equal to, after doing the math, 0.27554 joules per gram degree Celsius. Okay, rounding that, I mean, you can round, or you can leave the answer how it is. So let's just go ahead and leave the answer how it is on this one. All right, so then our last problem says a jeweler heated a sample of gold from 24 degrees Celsius to 45 degrees Celsius. The specific heat of gold is 0.129 joules per gram degree Celsius. If the gold absorbed 13 joules of heat, what is the mass of the gold? All right, so again, 14, what are my knowns? So I'm going to write out my knowns. I know what my mass, no, I don't know what my mass is. That's what I'm trying to figure out. I know what my delta T is. That is going to be 45 degrees Celsius minus 24 degrees Celsius to equal 21 degrees Celsius. My C value was given to me as 0.129 joules per gram degree Celsius. And my joules for the entire problem is actually my Q value, sorry about that, is equal to 13 joules. All right, so now same equation again. This time we're trying to solve for mass. That's the only piece of information that we're missing. So for this problem, I'm going to use that same equation like I said before. Q is equal to M times C times delta T. Plug in my known pieces of information. We got 13 joules is equal to, I don't know, mass times my specific heat, which is 0.129 joules per gram degree Celsius times 21 degrees Celsius. So anything on the right-hand side that's not M, I'm going to divide out. Do the same thing on the left-hand side. So I'm just going to divide this whole entire side by 0.129 joules, 21 degrees Celsius, and then we also have a denominator of grams degrees Celsius. Anything I do to the right side, I have to do the left side. So same thing, 0.129 joules per gram degrees Celsius, and again, 21 degrees Celsius as well. And extend that out. Again, anytime you have something divided a second time, it's actually the reciprocal, so everything gets kicked up to the numerator. So grams and Celsius are now on the numerator. The only thing that's going to cancel out are my degrees Celsius and my joules. So I'm left with grams, which is what I want. So after plugging this into my calculator, the mass that I should get is actually 4.7988 grams, and if I round that, that's rounded to 4.8 grams. That's your final answer. All right, I am going to go over this last problem and just explain it quickly. The other problems were pretty straightforward, but 15 asked, if you put a pizza oven into, the oven and all the temperature is the same on all the materials, but when you take it off, the crust is going to cool at a different rate than the cheese, right? And so this has to deal with something called specific heat. Specific heat, again, is the property of different materials out there that allow it to heat up or cool down at different rates, right? So depending on its specific heat is going to allow that heat transfer to either occur faster or slower. And so in this case, the cheese is probably going to have a higher specific heat. It's going to retain that heat energy longer than the crust because the crust is going to cool down a lot faster than the cheese. So that is directly related to, again, specific heat.